Okay, thank you, Ming. It's great to be able to be here and give the presentation, and at least to see all the familiar faces and see friends and colleagues. It's been a long time not being able to see everyone. So what I'm going to talk about today is the coupled interactions in superconductors, and mostly the ion superconductors. Heike Pufal has given a talk recently in this series already, talk about the pneumaticity tuned by strain gauge. So I'm going to talk about different subjects. I will try to say two things. One is the coupled interactions in ion selenide. The other will be how to engineer interface superconductivity in ion selenide STO and with LTO, STO interface in combination. I will go through when the work comes up, I'll acknowledge the collaborators. For the time domain experiment, really it was Simon Gerber, Shulong Yang, Patrick Kirchman, Wei Shen Li. Our thin film work really started with this with James Lee, Felix Schmidt, and a lot more. And some of the recent work really, so you contributed a lot. And now I'll touch one or two slides of the cuprates. That's a long-standing collaboration. And a lot of work here benefits from the interaction with Deng Hai Li and Tom Devlin. Okay. So let me, for the first topic, let me start out with ion selenide. That's the pressure dependence. That's the work of Jason Gu. And we know it's a low TC material. Under, I would say, modest pressure, the TC went up almost by a factor of 4 to 5. Okay. So this is very interesting. And when you look at more detail, it turns out that one of the most interesting things is, these ion selenium layers is the height of the selenium atom in this case, and the extremely sensitive function of this height. And you can see either different compounds, they go this way, or same compound under pressure. And that's the pressure dependence here, the red point. Now, this reminds me about some of the work Mingyi did when she was doing a PhD. And you can see that there's a sort of reminiscence of this sort of shape of the dependence of superconducting transition temperature. That is the horizontal axis is the boundary normalization, the vertical axis is the superconducting transition temperature. For different orbitals, that's the X, Y, Y, X, Z, Y, Z, and this is the X, Y orbitals. They all show this sort of shape. One wonders whether there are some underlying linkage between this kind of shape of TC dependence of structure, also the electronic structure. So the question really raises it appears that there's a linkage between correlation structural change and TC. And how one then question will be, what happens to the electrons if you move the atoms up and down? What happens to the electron-phonon interaction in the presence of strong correlation? Okay. So this has been a question I'm interested in for a long time in the cuprate context. So the challenge has always been how you would sort of go about measuring it. The traditional way of making electron-phonon measurements is subject to certain assumptions. For example, you can use Raman or optical and many other ways to measure it. You always need some sort of assumption, the Baire dispersion, density of space, something. So if people are not agreeing with your assumption, then they wouldn't agree with your conclusion. So the question will be, can we sort of devise a measurement that is a direct measurement, independent of this sort of assumption? So this leads me to the work we did using time-resolved experiment. In the time domain, you can possibly do some experiment now to achieve a precision which is not possible otherwise. So that was our goal. So the idea is that I'm going to move this selenium height up and down through some sort of excitation. Okay. So if I can measure this height change directly, and I can also measure the band structure change directly, both are direct measurement. By doing that, I'll be able to make a direct comparison of this, which will relate to a microscopic quantity called the deformation potential. So if you can do that, then of course you can try to extract information on the coupling strengths. Then you can also use that to gain insight about iron selenium physics. Okay. So the technique we're using is the combination of time-resolved formation. Here's a spectra. Instead of traditional formation with one photon, now you have two photons, one pump and one probe. And in this case, in a conventional formation, you only see states below the Fermi level. Now you can see that before your pump arrives, everything below the Fermi level. But when you now, if you do a pump probe experiment, you see states above the Fermi level because they were pumped up by the first photons. Then you can see the evolution of that. Okay, for example, how the direct surface state evolves in this particular example. Okay, so you can also actually use that to study driven system. But what we want to do here today is to use this technique to do a precision measurement of a ground state property. How are you going to go about doing that? In physics, at the end of the day, everything boils down to signal to noise. And we know a very powerful way to improve the signal to noise in physics is the locking technique. A traditional way, the locking is done at gigahertz type of frequency. So you can make a macroscopic measurement, but you cannot use that to make a microscopic measurement. So our goal was to push this locking technique into the terahertz regime and using the intrinsic frequency of the phonon in the system to generate a reference frequency, therefore to improve the signal to noise. So the idea will be try to use the IR pump and instead of incoherent excitation. If you're lucky, you actually can generate a coherent excitation. In this case, you of course can now generate a reference signal. Now you use X-ray to measure the lattice constant and use time-resolved photomaking to measure the band structure. Combining these two will give you the information of what you want, the deformation potential. So here's the plot showing the pump probe X-ray diffraction intensity. And you can see that aside from this sort of background, you see a beautiful oscillations of the vibration, in this case, the time domain in the time frequency. And if you do a Fourier transform, indeed, you see a mode, the A1G mode, and at a frequency of 5.33 terahertz. Okay, so this will allow you to learn something about. We're pretty lucky that Raman scattering is done in this case, and it turns out this mode is exactly the vibrations that are moving these atoms up and down. So that's what we want. Okay, so here is a time-resolved photomation experiment, and you can see here. I hope you see the vibration of the photomation spectra as a function of time. Okay, let me try to run it once more. I hope you can see the vibration of the photomation spectra. That's sort of 1.5 picosecond time scale. And if you now put these two together, the upper ones is the vibration of atoms up and down, And please look at the scale. It's a very, very small. It's from here to here, it's 0.8 picometer. It's far less than an angstrom. This constraint, as you will see later, we know that a typical material have a lattice constant at about a couple angstroms. So you better not change the lattice constant by 1% or more, because chances are if you change the lattice constant by more, you may well be studying different material, not the material you intend to study. So that constraint, and given the fact that this is less than 0.01 angstrom, and given the signal to noise, you can see this technique can give to you. That's the power of diffraction. Now you can see that simultaneously you see also the signal from the band structure, in particular the top XZ and YZ band show similar oscillation. Okay. So now if you put this together, then you can see that. Now, as I said earlier, we want to make a ground state measurement. That means you need to ensure that you are in a linear response regime. And this shows the fluence dependence of this amplitude of delta Z. You can see that as the fluence going towards zero, the amplitude also going to zero. So you are in a linear response regime, and same thing extrapolate the band structure. Now, if you take the slope of this one and the slope of this one, then you divide them, and you end up in a situation you can try to learn something about the deformation potential. Okay. So it turns out that the deformation potential in this system has been calculated. Both the density functional value is about 1.6, or the dynamic mean field theory, where the strong Coulomb correlation is more explicitly taken into account. This theory work is done before our experiment. And you can see that the experiment agrees with the dynamic mean field theory much better than the density functional theory. What the extrapolation, of course, is to say that in this context, you have to take into the correlation effects to get to the experimental result. Also, it says that the strong Coulomb interaction actually significantly also enhance the deformation potential. Therefore, also the electron phonon coupling. So it's to say that in those coupled systems, they have a lot of ways to influence each other, and that probably is really the underlying reason of the richness of physics in this system. Okay. Now, we are also in this context looking at what you try to benchmark this technique more, and you can see that the photoemission spectrum on the left-hand side, you see the time dependence of the photoemission spectrum. Those are picosecond time scale in unit, and if you take a cut, then you see all those oscillations. And if you do a Fourier transform, and you can see the two A1G phonon vibrations in this system. Again, it's convincing because you see all the phonons in the electron spectrum, okay, through the electrons. Those are all work in progress. Now let me come to the second subject, namely the interface engineering. Our work really have benefited a lot from the contributions of Donghui, Makoto, Hashimoto, and a lot more. When Rob was still at Stanford, now he moved to Oak Ridge. And you can see that's the beam line, and that's the MPE system. It took a lot of effort to set it up. And so the example I'm going to talk about is the case of one unit cell on selenite. That's the same compound which I mentioned earlier. And by the way, the earlier experiment the femtosecond locking experiment was also done on thick iron selenium films. The bigger the films have a better, larger size for this sort of experiment. But now I'm going to talk about single layer, so it's a different subject. We were motivated by the work of Chicken Xue's group in Tsinghua University. And in their case, you can see that what they find is if you grow iron selenium one monolayer on top of Strong-Syn tightening, okay, what you find is that this system actually has a gap is about 20 millivolts, so it sort of is a really much higher superconducting gap than one would have expected from the TC of the system. As I said earlier, the bulk form is about only 8 Kelvin. So that generates a lot of excitement. So we also looked into that. And we tipped at many other groups to find out that we can see the Fermi surface, which is a pocket near the Brownian zone corner. Okay. But what I want to focus on here now is a different feature. Let's say if I make a cut across the Fermi level, I see a band structure, look like this. Look at the panel C. Okay, you see a band sort of electron pocket in this way. But when you look carefully, you see a copy of this band here. You see a copy here. Okay. Now, if you do to enhance that, you can do a second derivative. You see the original band A, and you see its copy A prime. Here you can also say I see a band B, and it's copy B prime. And you will say, well, where is it? It's so noisy. When in doubt, go back to the original data. You can see, you may question whether there's another feature here. But when you go back to the raw data, I hope you'll be convinced that there's a feature here. That's the B prime. So there's a copy of this being shifted by almost 100 millivolts in frequency. And the copy is very loyal in the sense that you can see the subtle band back, that is the superconducting gap, okay? And the copy had the same thing. This work shows that this sort of phenomenon of replica copy happens only in one unit cell. If you go to 2 unit cell or 30 unit cell, this sort of replica phenomenon goes away. Okay. So the 1 unit cell has something special about it. Here you see the temperature dependence, and you can see that it's at 10 Kelvin, 30 Kelvin, 50 Kelvin, 70, 90, and 120. You don't see any change. Okay, this certainly is not related with the superconducting transition. 90 Kelvin is clearly above that. Okay, so what is it? And it was inspired by the idea of Damhai Li. We think this is a result of electron-phonon coupling. So if I'll make a cut and you can see the original band, then sort of replica band. And with the lover's eye, you may even see a feature here. Indeed, the more recent work by the Cornell group, Carl Shen, they have analyzed this feature and actually gained more insight. So that the lower part is the formation spectra of hydrogen atom. I should say that this sort of behavior as a second, as a peak, the main peak and a satellite peak, another peak. This sort of behavior is very rare in solid. In gas, you see it; it's extremely rare in solid. And the interpretation is this replica really is a coupling of the interface phonon with the Strong-Syn tightening phonon. In this case, it's about almost 100 millivolts. So they suggest that there's strong interaction between the film and the substrate. This is the reason why this play a role enhance TC in this way. That's their original work. One of the key things I want to stress that this analysis really shows that it's a small Q forward scattered phonons, just like a capacitors in this sense. Okay. Now, Deng Hai and Tom Devereaux's group have done more analysis. They assume some sort of electronic pairing for the film itself, and with these additional channels, it can give 50% boost to superconductivity. Okay. The group has since refined the theoretical work, and I just want to reference that there's a blue shift of the mode, and also it appears to require smaller coupling constant to do the same thing. So experimentally, I just want to make one contact in this work with our recent work on the cuprates. In the cuprates, it's in the same way. We find that, I wouldn't go into the detail, there is a feature in the formation spectra, this sort of depth in the spectra, which is a coupling feature. And if you monitor this, as you go from high doping to low doping, you see your TC superconducting gap changes by a factor of 4 in a very narrow doping range. It turns out in the same doping range, the pseudo gap phenomenon changes a lot. Also, the electron phonon phenomenon changes a lot, all in a very narrow doping range. So the idea will be all those interactions sort of forming some form of flying wheel, one may say, and they enhance each other. So in that spirit, those coupled interactions probably doing something similar here. Now I want to go back one more thing to say that you can see a more refined experiment with study on different substrate and different orientation, and realize that in fact the iron selenide on monolayer have two things. One aspect is the charge transfer, which I have not touched about it. The other is the monolayer. In other words, if you look at charge transfer or doping of the system, you can get them to 40-50 range, but in the 60 range, you need additional the interface phonon contribution. So more recently, we did a more study. So the question will be where is doping coming from? And if you put iron selenide on substrate, then of course there's band bending and charge transfer, this phenomenon that's very typical. So what we want to do is to use the Langston tightening and Stromsen tightening as a platform. What they say is that if we start with Stromsen tightening and grow different thickness of Langston tightening, you have a different amount of carriers, charge reservoir to dope in your film. This way you can dope the same film, but maintain the interface quality to be consistent. So that's what we did, and just to say that we can grow LTO on STO in an architectural way, and we can also grow iron selenide on top of that, depending on with the thickness of LTO being adjustable. Okay. So here are some of the data. Okay. Look at the Fermi surface of those films. The lower part of the Fermi surface of the STO substrate, that's a 1 unit cell, 3 unit cell, 20 unit cell of LTO on top of that. Okay, and you can clearly see that as you grow the grow the LTO thickness, you can see the detail doesn't matter, but there are more and more electrons at the surface. That means there's more potential for charge transfer. On the other hand, if you put the iron selenide on top of that, you find that independent of the amount of carriers at the surface of the substrate, the Fermi surface of the iron selenium remain to be identical. So in other words, even though your substrate, you can see the electron density at the low thickness changes a lot, but the carrier density as measured by the Fermi surface, as well as the superconductivity as measured by the gap, seem to be completely robust in this system, almost as if there's a magic doping in this system. Here we compare our work with some of the earlier work of potassium and lithium intercalation. You can see that in the case of those intercalation work, they find the superconducting transition temperature are actually discrete, okay, either at this TC or this TC. And in this case, and they have both potassium and lithium in this case. Okay. Our work suggested doesn't matter how many carriers in the substrate, the doping in the systems appear to be completely anchored, and also superconductivity is. So this also explained in the literature, there's so many groups working on the film and growth, they always ended up with the same doping, same TC in this system. So that is very intriguing. And we have some ideas, and this is telling us that we are far from understanding selenide. We have some ideas about the phase diagram, but I think my time is over. Let me just put this up to summarize. We try to say that the multimodal ultrafast technique, the terahertz blocking permits the precision measurement of coupled interaction are not possible otherwise. Suggest interaction in electron-electron interaction, enhanced electron-phonon interaction. Then interface engineering also gain insight how the coupled interaction enhance superconductivity in the system. So let me now stop sharing and.
Thank you very much.
Great, thank you. Yeah.
Thank you. Fantastic talk. I guess anyone have any questions? You can raise your hands. I guess while we're waiting, Zex, may I ask what are some of the potential mechanisms in which the doping is pinned?
Yeah, we have a speculation with the iron selenium system may have another insulating phase nearby, and the barrier to enter that is higher. Therefore, even though we have a lot of electrons at the interface ready to go in, but it couldn't overcome that barrier. And in a more disordered system like potassium or lithium sort of doping, then things are rounded off easier. That's probably the reason, because with the way doping through interface, it's a fairly clean. So I would say it's a more clean limit. But I think it's more of a puzzle than an answer yet. But that's how research goes. Yeah.
I see.
Amalia, hi.
Amalia, yeah, you wanna have a question?
Hi. Very good talk. So my question is more about electron phonon coupling, and if there is any other ways in which we can kind of establish some tests for it, like an isotope effect type of test, in which we can put all the experiment and data together to get it sorted, because we also speculated about the role of acoustic phonons that might affect criticality. So I just wonder, how do you see these phonons really manifest, and what type of phonons might be relevant?
We definitely know that strong correlation is very important in iron selenide system, but since you asked about isotope effect, in iron selenium, iron-based superconductors, there's a very strong isotope effect in the system. With alpha is pretty value pretty big. It's about 0.4. Right? So in that system. On the interface work, that has been, there's isotope exchange of oxygen in that work, and shows that indeed the replica is a phenomenal type of a feature. I do not follow exactly what you mean by criticality. I guess if there's a particular theory or particular idea you have on this subject. So.
No, I was wondering if there is a difference between acoustic and other type of phonons which you have in mind when you think about what influences your results.
Now I got it. Yeah. Now the phonons we are looking at here are all optical phonons. Okay, one is about 5.3 terahertz, and one is just very high frequency. It's almost 80 or 90 millivolts. That mainly had to do with our ability to see them. In the sense that those are the phonons which are very visible in the experiment we're doing. But what we wanted to do in the first set of experiment is to say that, can we benchmark in one case a experiment that we can get the critical quantities directly from experiment, so that we do not need an assumption. And in that case, then you can say you can make a more direct comparison with the microscopic calculations.
Yeah. Thank you.
And then I think Elia, a question.
Yes, thank you very much, Dix, for a very nice talk. I have two related questions for the first part on the iron selenium. The first, when you said that there is this big difference between DMFT and DFT, if I try to boil it down, does it, I mean, in a simple terms, does it simply correspond to the fact that if you compare DFT and DMFT, the sizes of the pockets that you get in iron selenium are very different. So if I would just shrink the size of the pocket and would compute, within the effective series, the effective potential, it's just needed that I need to have a much smaller pocket to get the right number for the deformation potential. That's just a clarification question. And another question is that when you do the measurements in iron selenium, I understand that you do it starting from the nematic phase. So in principle, nematicity can affect also this strength of the deformation potential. So in this regard, I know that there were also measurements done for the 1 to 2. You also cited that. So do you know how large, is there any difference in the deformation potential if you compare it, let's say, nematic state and 1 to 2, where you don't have, for example, nematicity, or in any of the compound where you don't have any nematicity?
Okay, on your first question, it's probably a more detailed look at what it means in the calculation. You probably are right on that, and what will be the mechanism. One particular thing I like about the dynamic mean field theory, two things. One is it's a very different prediction on this quantity from the other calculation. And I also found that that theory is done before the experiment. B is that if you really look at the coupling modes, they predict one thing which is very non-trivial, the non-monotonic change. They kept, remember the pressure dependence of TC or the coupling is a non-monotonic. And that non-monoticity is non-trivial, and that appears to be captured in this calculation. As for your second question, okay, my take will be, indeed you are in a particular experimental phase, and the nematicity is there. My take will be that probably doesn't matter as much. That'll be my guess. I can't prove it. Okay.
Okay, thanks. Thank you.
And Henri?
Yes, sorry, I arrived a little bit late. Zach, but
Great
I
seeing
like
you, Zhao.
I liked your the end of your talk. Just a simple question: Do you pretend that the superconductivity is due to electron phonon behavior in that case?
In the monolayer system,
Yeah.
or no, we in the monolayer system, our working assumption was there is a pairing mechanism of itself, and we actually do not necessarily know exactly what it is, but in our analysis we assume it's of electronic origin. Then we say, if there's a superconductivity already, what will a small q phonon do to such a superconductivity? And the way the reason we know it's a small q is that I have a band structure and I see a shift. Remember, I said I have a loyal copy of the two. Okay, and if the phonon q is non-zero, then I have all momentum mixed up. I will not have this detail being copied. That dictates the q is small. As you know that small q can enhance superconductivity of electronic origin or phonon origin the same.
Okay. That could be a little bit similar to what we think in the case of cesium-360 in the full arrays,
Yes.
in which we have a high TC, a near remote transition, and it could be that it is an enhancement due to the correlations.
Yes, I think we would just. I'm interested in the systems. They seem to have more than one thing going on, and I'm thinking that those are lucky cases. The more than one thing actually help each other. They don't often do. They usually go against each other, but occasionally they do help each other, and that's probably why. Yeah.
The last question by Qimiao.
Yeah, it's just a quick follow-up to what Ming asked. So experimentally, when you change a substrate, you said the Fermi surface doesn't seem to change.
Yeah.
Is there anything that changes, say, effective mass or the bulk FERC, for instance, there's some high energy features interpreting terms of low Hubble band, anything in the spectrum?
Okay, there's a lot of change before we put on iron selenium. Okay, you can see Fermi surface is changed by a factor of 4. Okay, so as we prepare different substrates, but somehow once you put an iron selenium, it doesn't matter how many electrons are on your surface to be doped. They end up with the same. These still need to be more work to be done. And as you can see that the level of question you're asking, the Fermi surface, the Fermi velocity and all that, probably the error is too big to see any difference yet. But my guessing, now I'm guessing because it's a big error bar. I'm guessing it's not going to change much because the superconducting gap doesn't change much.
Very interesting. Thank you.
I guess, if I may, as a follow-up question, yes, I'm imagining the strain on the iron selenium is also changing by the different substrate. Is that true?
No, the tuning, what you're referring to Heike's work, those are crystals, not a substrate. The strain tuning. That's what you're.
I'm in the epitaxial strain for the last part. The different substrates, they may force the monolayer to have it.
No, that's the earlier work. Strong titanium has many things special, like lattice constant, dielectric constant, a lot of things. So we did work on different surfaces, 100, 111, 110. They all look the same. And also there's a titanium oxide. They all look the same. So then it boiled down to a question, whether the chemistry of there are two possibilities. One is the strain doesn't matter, will be one answer. The other is the chemistry of the system is such that it always, like in the end, it forms some sort of magic interface. Okay, in that case, you may start out with something you think is very different, and your naive expectation, you will say you end up with something very different. But in fact, when the films are grown after the cooking, the annealing and all that, you end up with the same thing. That's also possible. That will be another magic type of thing. And this is still, I think this is very rich, but it's still working in progress.
Thank you very much. Thank you, Zeus, for your time. Thank you so much. I guess we'll move on to the second part. Thank you, Igor, for your patience as well. If you may start sharing your screen.
All right. So let me start the presentation mode. So is it in the presentation mode currently? Oh, now it is.
There it is.
Right.